Today, we're going microscopic to figure out why the world around us, well, why it works the way it does. We're going to look at a fundamental blueprint that's written at the atomic level, but it defines pretty much everything we see and touch. I mean, have you ever really stopped to think about it? Why is a diamond one of the hardest things in the world, while a rubber band is so stretchy you can fling it across the room? Or why does a ceramic plate shatter into a million pieces, but a metal fork just bends? You might think, well, that's just how they are. But the real secret, the underlying code that governs all of this, is hidden at a level we can't even see. It all comes down to this universal dance happening between individual atoms. All right, so here's our game plan for this explainer. We'll start with that atomic push and pull, then we'll see how they find their little sweet spot. After that, we'll learn how to read the energy blueprint. From there, we'll see why materials get stiff, how they handle heat, and finally, how this is basically the code for, well, everything. First things first, the fundamental forces. Everything, and I mean everything, starts with this simple interaction between any two atoms. This one graph, believe it or not, tells the entire story. See, it's not just one force acting on atoms. It's a constant tug of war between two competing forces. And that balance changes depending on just how far apart they are. So on one side of this tug of war, you've got an attractive force. That's the blue dashed line you see, Fa. This is what pulls atoms towards each other when they're a little bit apart. You can think of it as the cosmic glue trying to hold all matter together. But there's a limit. You can't just squish them together. If the atoms get too close, their electron clouds, which are negatively charged, start to overlap. And just like trying to push two magnets together the wrong way, this creates a massive repulsive force, that's the red line, Fr, that just skyrockets and shoves them apart. This is literally what keeps you from falling through your chair. So, with all this pushing and pulling going on, how do atoms ever just settle down? Well, they find a balance. They find their sweet spot. Now, if you add those two forces together, the attraction and the repulsion, you get the net force. That's the green dashed line here. And check this out. There's one magic point, one specific distance where the attractive pull perfectly cancels out the repulsive push. It's right where that green line crosses the zero axis. The net force is zero. The tug of war is a perfect tie. We've got a name for this perfect distance. It's called the equilibrium spacing, or R0. This is the sweet spot. It's the most comfortable, most stable, and most natural distance for these two atoms to be. It's their home base, and it's where they'll always try to be. Okay, talking about forces is super useful. But, a lot of the time, it's actually way easier to think about all of this in terms of energy. They're really just two different languages describing the exact same thing. So, all that pushing and pulling we just talked about, it essentially creates a kind of landscape of potential energy that the atoms live in. And here is that landscape. This bottom curve shows the net potential energy. Notice something familiar? The absolute lowest point of this energy well or trough lines up perfectly with that R0 spacing we just found. It makes sense, right? Nature's kind of lazy. It always wants to be in the lowest possible energy state. For these atoms, that's their stable home. Now, the depth of this well is a really big deal. We call it the bonding energy, or E0. It's basically a measure of how much energy you'd have to pump into the system to break that bond and pull the two atoms completely apart. So a deeper well means a much stronger, much more stable bond. Okay, so that's the micro-level stuff. Forces, energy, sweet spots. But why should you care? Well, this is where it gets really cool, because this is how we connect that atomic blueprint to real-world stuff, like stiffness. Yeah, the source material here really hits the nail on the head. A material's stiffness, what engineers call the modulus of elasticity, is at its core just a measure of how much its atoms fight back when you try to pull them apart from that comfortable sweet spot. And you can see it all in the shape of our force curve. Just look at the slope right where it crosses zero. If that slope is super steep, it means you have to apply a ton of force to get even a tiny bit of separation. That's a stiff material, think steel or diamond. But if the slope is more gradual and shallow, it doesn't take much effort to pull them apart, and that's your flexible material, like a soft plastic or a rubber. And what's just mind-blowing is that this same exact model also tells us how materials behave when they get hot. Let's uncover the secret behind thermal expansion. The absolute key to understanding this is in the shape of that energy well. It turns out it's not perfectly symmetrical. For real materials, like on the left, the curve is steeper on the inside and a little shallower on the outside. It's lopsided. Now, if it were perfectly symmetric, like that ideal version on the right, materials wouldn't expand when you heat them up. At all. Weird, right? So why does that asymmetry matter so much? Well, heat is just energy, and it makes atoms vibrate back and forth more and more. But because the well is lopsided, it's easier for an atom to swing further outward than it is to swing inward. This tiny difference means their average position actually shifts a little further away. Now multiply that effect by trillions and trillions of atoms all doing it at once, and boom, the whole material expands. So it all comes back to the shape of that energy trough. If you have a material with a deep and narrow trough, think ceramics, that means it has a really high bonding energy. And because that well is so tight and narrow, the atoms can't vibrate very far. The results? Very low thermal expansion. All right, let's just step back and put it all together. It is truly amazing how this one simple, elegant model of how two atoms interact can predict so many different and complex properties of the materials all around us. This table just lays it all out so clearly. A deep, narrow trough means high bonding energy. That corresponds to a steep force curve, which gives you a high modulus of elasticity, a really stiff material. And it also means low thermal expansion. Now look at the flip side. A shallow, wide trough means low bonding energy, a low modulus, a flexible material, and high thermal expansion. It's all connected. It's all right there in the same atomic blueprint. So at the end of the day, this isn't just theory. It's a predictive tool. It's the fundamental code. Understanding this blueprint, knowing what makes something strong or flexible or stable when it gets hot, that opens up a whole universe of possibilities. It really makes you wonder, if one simple graph can explain all of this, what incredible things could we build if we start designing new materials atom by atom?